Dear students, in oscillation now we are going to something new. We are having a topic called as composition of two simple harmonic motion. Initially we deal with linear simple harmonic motion of the particle, that is a single particle performing linear simple harmonic motion, that is starting point. If we are knowing the starting point, if we are knowing the amplitude and time period, we can find displacement of the particle. Right? For example, pendulum we are having a pendulum that is starting from here, it goes to the extreme, it comes back, one oscillation. So that is a single particle. Now we are having two particles. So it is called composition of two simple harmonic motion. Like superposition of waves. We are having when two or more waves arrive at a point. When suppose there is a light here and when two sources of light, and when the lights are coming from the two sources and when it is meeting at a point. So the resultant displacement of the light, that is called superposition of the wave. So as superposition of the waves we are having, in analogy to that we are having composition of linear simple harmonic motion. Let us consider, suppose we are having one pendulum. Suppose there is a rod. We are having one pendulum, another pendulum near it, tied to the string, and again one more pendulum, that is third pendulum. Three pendulums. So we are having a rod, and then in rod, suppose we are having a single rod is there, and it is made of a metal, and then we are having length of that pendulum is same. And suppose we are having two pendulums, that is three pendulums in a line, and suppose the pendulum starts from right extreme. The another pendulum, which is the second pendulum, suppose it is again going from the right extreme from here. Suppose there is one pendulum here, second pendulum is here. It will start oscillating. Release it. It starts oscillation. You can just see it is oscillating, and when it is oscillating, due to resonance, what happens? The third pendulum will start oscillating on its own because there is resonance. Okay, because we are having a metal rod, and then to the metal rod we are having three pendulums which is attached to the metal rod, and when the two pendulums starts oscillating with the same time period. See, what is happening here is the same time period. Time period is same. It is starting from one is starting from here and one is starting from here. So amplitudes are different, but what is happening here? The two pendulums which is there, it is performing linear simple harmonic motion. So the third pendulum which was there, it will start oscillating on its own due to the resonance. So what will be the resultant displacement of that amplitude? What will be the resultant amplitude? So what will be the amplitude of the third one? And when it is going to start? Its phase. Where will be the starting point? When it is going to start? When these two pendulums are already oscillating. So basically it is composition of linear simple harmonic motion what we are going to learn. So let us start with the derivation part of that. Composition of two simple harmonic motion having different amplitude but same time period. So what will be the resultant amplitude we will see for the third one? The resultant displacement is given by what? We will see. So when two particle performing linear simple harmonic motion along the same path with different amplitudes and same time period, the resultant displacement is due to the superposition of two linear simple harmonic motion. So what will be the resultant displacement? What will be the amplitude of the resultant displacement and what will be the phase of the resultant displacement? Let us start. So let us consider the first particle having displacement. The equation is given by x1, that is amplitude of this first particle is a1, having sine omega t plus pi 1. Omega 1 I am not omega because same time period है. Pi 1 इसका phase है, इसका starting phase है, और amplitude is the E is the amplitude of the first particle. Second particle we are having same things, x2, which is a2, amplitude a2. It can be different in amplitude a1. I told you, but time period is same. So I'm not writing omega 1 in omega. So time period is same condition. Plus we are having y2, starting point of this. So the particle can start from this side also, two particles, and then third particle will start oscillating. Same thing, the particle can be in the opposite side also. Can be in the opposite side also, and the third particle will start oscillating with some amplitude. So we are having x1 and x2. The resultant displacement is, that is x. Resultant is the vector sum of the displacement due to two particles. So the resultant displacement, the third one, is the vector sum of the displacement of both the particles. X is x1 plus x2. Vector sum we can just put, but in magnitude just I am writing x is x1 plus x2. You can put bar also. X is x1. What is x1? We are having a1 sine of omega t plus pi 1 plus a2 sine omega t plus pi 2. Let us solve this. X is, we are having a1 sine a plus b sine a cos b plus cos a sin b. a1 will come here plus same thing about this a2 sin a cos b plus cos a sin b. What is common in this? So this is the resultant displacement due to both particles. X is, what common thing can you take from here is we are having sin omega t, and here we are having cos omega t cos omega t. So we can write directly in the bracket a1 here, we can write a1 cos pi 1. So we are having from here sin omega t is common, a1 cos pi 1 plus a2 cos pi 2, bracket common is sin omega t, plus similarly here we can write a1 sin pi 1 plus a2 sin pi 2. The bracket, what is common in this? Cos omega t. Now here more further we have to assume. You cannot solve this. Now we are taking, let this part a1 cos pi 1 plus a2 cos pi 2, which is equal. In a1 is the amplitude of the first particle, a2 is the amplitude of the second particle. So जो third वाला जो resultant होएगा a1 a2, that is called, दोनों का resultant, that is r. It can be more or it can be less amplitude. Cos and cos is there, so we can assume it as cos. And phase उसका pi 1 था पहला particle का, pi 2 का second particle का phase, and third resultant जो phase start होएगा third particle का, ये pendulums बताया आपको, that is delta. So here I am considering this is equation number 1. For 1. Let similarly also, and here also I am assuming this thing, जैसे कि मैंने assume किया इतना, तो ये अभी मुझे assume करना है a1 sin of pi 1 plus a2 sin of pi 2. We have to assume because the derivation we are deriving mathematically a1 a2, so resultant आपका r आएगा थर्ड वाले का, रिजल्टेंट जो है दिस एम्पलीट्यूड, साइन साइन है तो साइन आएगा, और उनका फेस पाई 1 पाई 2 है तो इसके बदले में आपका डेल्टा आएगा. ये मेरा सेकंड ऑर्डर, आई एम गोइंग टू यूज दिस. Therefore this equation will, therefore x becomes, आपका जो x है वो क्या बन जाएगा a1 cos अल्फा, ये क्या बन गया आपका r cos अल्फा, ये आपका साइन ओमेगा टी, प्लस दिस इज बिकमिंग r sin delta. and then this is cos omega. If you solve this, x is r is common दोनों में से. Again you are getting the same formula, sin a cos b plus cos a sin b. So I am getting sin a plus ये जो आपका मिला है, ये देखो, ये पहला पार्टिकल का, ये दूसरा पार्टिकल का. सो रिजल्टेंट जो तीसरा पार्टिकल जो पेंडुलम का केस बताया, फर्स्ट एंड सेकंड, थर्ड पार्टिकल स्टार्ट ऑसिलेटिंग विद द रिजल्टेंट डिस्प्लेसमेंट x. सो दिस इज द x फॉर द थर्ड कंपोजिशन ऑफ 2SHM. कंपोजिशन है x इज r sin omega t plus delta. So that is resultant displacement. r is the resultant amplitude. दोनों का resultant amplitude r है. Now going for resultant amplitude r. Squaring and adding equation 1 and 2. Here squaring and adding, right hand side is r square sin square delta plus r square cos square delta is equal to, left hand side we are having, squaring this, a1 sin of pi 1 plus a2 sin of pi 2 whole square plus a1 cos of pi 1 plus a2 cos of pi 2 the whole square, that is equal to r square sin square delta plus cos square delta will give you 1. So r square is common, therefore we are having r square. A plus b the whole square, so this becomes r square, sin square plus cos square is 1. Now this right hand side we are having equal to sign here. We are having this a plus b the whole square, we are having a square plus 2ab plus b square same thing here for this one, plus a square plus 2ab plus b square solving further. Therefore r square is equal to, take common in this, a1 square pi, another it is here cos square pi. So that is a1 square sin square plus cos square is 1, so we are getting a square plus we are having this a2 and this a2, pi 2 and pi 2, so a2 square and a2 square common, sin square plus pi cos square is 1, so we are adding a2 square, a1 square, a2 square plus the remaining is, here we are having 2a1 a2 and here we are having 2a1. So remaining we are writing, taking common 2a1 a2. In the bracket we write cos A cos B. First we'll write this cos pi 1 cos pi 2 plus we write sine of pi 1 sine of. Solving it, we have seen, we solve that. R square which is equal to, wow, this one A1 square plus A2 square plus cos A cos B plus sin A sin B, cos A cos B plus sin A sin B is cos A minus B. And having the formula, okay, cos A cos B plus sin A sin B, that is 2A1 A2 cos of pi 1 minus pi 2. So R is resultant amplitude is given by under root of A1 square plus A2 square plus 2A1 A2 having cos of pi 1 minus pi 2. So this is a formula for resultant amplitude. So the third one, the resultant amplitude depends upon amplitude of the first one, amplitude of the second one, depends upon phase of first one, phase of the second particle. So R is under root of A1 square plus A2 square plus 2A1 A2 cos of pi 1 minus pi 2. Cases, in very short I am just telling you cases. What are the cases? If pi 1 equal to pi 2, if both the particles are in the same phase, for example if both the particles are in the same phase, okay, so what is the resultant amplitude you will get? Amplitude resultant A. So if they are in the same phase, pi 1, pi 2, so what is cos pi 1 minus pi 2? So we are having cos pi 1 minus pi 2. Yeah, what is cos pi 1 minus pi 2? It will be equal to pi 1 pi 2. So cos 0 is 1. So if they are same, so pi 1 minus pi 2, we will be having cos of pi 1 minus pi 2, it will be 1. If they are in the same phase. So what we are going to get, therefore we will get resultant amplitude R, which is equal to under root of A1 square plus A2 square plus 2A1 A2 cos, if they are equal, cos 0, directly we can write pi 1 pi 2 cancel, we will get 2A1 A2. They are equal, they are in the same phase, we can write R which is equal to, that is under root of A1 plus A2 the whole square, square and square will get cut, we will get A1 plus A2. So if they are in the same phase, resultant amplitude is directly A1 plus A2. Same case 2, we are writing, if they are in the opposite phase, or if they are in the opposite phase. What is the meaning of the opposite phase? Is they are in the opposite phase. So phase difference is 180 degree. Pi 1 minus pi 2, if it is 180 degree, here pi 1 minus pi 2 was 0. Here pi 1 minus pi 2 is 180. So resultant amplitude what you will get is under root of A1 square plus A2 square cos 180 is minus 1, we will get minus 2A1 A2, and that will give you under root of A1 minus A2 the whole square. We will get resultant amplitude is mod of, I'm adding A1 minus A2 because A2 can be also more, A2 minus A1 or A1 minus. Case 3 we are having. So we are having these cases. We are having third case. Yes. Case 1. We are having case 2. Then we are having third case. What is case 3 we are having? Case 3 is if pi 1 minus pi 2 is 90 degree. That is pi by 2. So the particle is here, here one particle. If the particle goes here, this will come here. If it is going here, it is going to come here. So phase difference of the two particles are 90 degree. We are having phi1 minus phi2. We are having resultant R is equal to, what is phi1? What this equation become? Cos 90 will become 0. This will become under root of a1 square plus, because cos 90 will be 0, so you will get a1 square plus a2 square is the resultant amplitude of composition of two simple RMA equations. So these are the cases of this. The cases you can include in your exam. Depends upon, you can write till here only, then we can go for the phase. So we are having resultant amplitude. We have seen all this. Now we will go for resultant displacement. So let us go for resultant displacement. I am just rubbing this one. They are going for resultant displacement now. Resultant displacement, resultant phase, difference, resultant phase, not resultant phase, resultant amplitude, or resultant phase divided by delta. Equation 1 and 2 you can divide by dividing 1 by 2 or 2 by 1, we are getting R sine of delta upon R cos of delta, that is A1 sine phi 1 plus A2 sine of phi 2 divided by A1 cos of phi 1 plus A2 cos of phi 2. RR will get cut, we get tan delta. Tan delta is again we are adding A1 sine of phi 1 plus A2 sine of phi 2 divided by A1 cos of phi 1 plus A2 cos of phi 2, and hence Canada delta is tan inverse. If you want to find resultant phase difference of composition of SHM, delta is tan inverse. Finally we write A1 sine of phi 1 plus A2 sine of phi 2 divided by A1 cos of phi 1 plus A2 cos of phi 2. So by dividing equation 1 and 2, we got resultant phase. Formula for phase difference delta is depends upon your tan inverse A1 after the first particle, after the second particle, and their phases phi 1, phi 2, their starting point. So resultant is delta is tan inverse A1 sin phi 1 plus A2 sin phi 2 upon A1 cos phi plus A2 cos